Hi everyone, it's me Rohit. I'm going to be explaining an Aime problem. This one is actually from the 2013 Aime I, and it's actually number 12. Um, so let's take a look. Over here we have the diagram, and let me actually read the problem off to you.
Let triangle PQR be a triangle with angle P equals 75 degrees and angle Q equals 60 degrees. A regular hexagon ABCDEF with side length 1 is drawn inside triangle PQR so that the side AB lies on PQ, side CD lies on QR, and one of the remaining vertices lies on RP. There are positive integers A, B, C, and D, such that the area of triangle PQR can be expressed in the form A plus B root C all over D, where A and D are relatively prime, and C is not divisible by the square of any prime. Find A plus B plus C plus D.
Here we have our triangle PQR, and as you can see we have our regular hexagon. And the important thing about solving these problems is that you will always have to draw a really nice diagram, because a really good diagram, well, it does a couple of things. One, I guess it looks nice, but the other thing is it could help you see things that you probably couldn't see if you just broke out a diagram without a ruler, maybe. Just really accurate diagrams help you see things clear. So let's start. So you'll notice that I've actually labeled the diagram already. We have 75 degrees over here at P. Q is 60 degrees over there. And R is also 45 degrees because, well, it wasn't given in the problem, but because the three angles of a triangle add up to 180 degrees, we do know that angle R is in fact 45 degrees. Let's start by finding out things that we do know. We know that angle A, or PAF, is in fact 60 degrees because BAF is 120 degrees, so PAF is 60 degrees. So let's write that down. And then we also know that PFA, angle PFA, is 45 degrees. So because we know that three angles of a triangle must add to 180 degrees, so let's get that. And now what you'll actually notice is that we have a few interesting angles here, like PAF is equal to angle Q, and PFA is also equal to R, as shown in the diagram. So what this actually means is that, well, first off, it implies that AF is parallel to QR. So let's write that down over here. But this also has like another implication. The two triangles are similar because all the angles are equal. So we know that triangle PAF is similar to triangle PQR, and this is by angle-angle similarity. Okay, so and we also know that AF is equal to 1. So we can also label this AB equals 1 because it's the side of the regular hexagon. And now, something that we can also get out of this diagram is that, well, we look at triangle QBC, and it looks a lot like an equilateral triangle. And that's probably because it is an equilateral triangle. As we know, angles QBC and QCB, these are also 60 degrees because they are exterior angles of the hexagon. So let's go ahead and write that. So this makes the triangle equilateral. So we can make those marks on our diagram. It's good to keep track of things on your diagram so you don't forget. And that also means that QB and QC are also length 1. So we can mark that as well. Now, so let's look at our whole diagram now. We want to find the area of triangle PQR, which is the big triangle in the diagram. It's the very large triangle that you see. And, well, how are we going to do this? We have two similar triangles, though. We know that triangle PAF is similar to PQR. So what we can do is actually, if we can find the area of triangle PAF, then the ratios of the side lengths between PAF and PQR, then maybe we can, through that sort of relation, we can find the area of triangle PQR. So let's try and make that happen. But to do that, we need to look at triangle PAF. So what do we know about triangle PAF? Well, we do know that it's 75, 60, 45, but this is also a little bit of a special triangle, and I'll show you what I mean. We'll be able to determine the side lengths of this triangle very soon. So let me show you triangle PAF. Alright, so here we have triangle PAF. This is enlarged. We do know that AF does in fact equal 1 because it is the side of the regular hexagon. And notice what I've done here. I've actually split the triangle into two special triangles that we know that we can easily find the ratios of. So one is a 30, 60, 90 triangle, and the other is a 45, 45, 90 triangle. So we can actually mark up our diagram a little bit. So let's go ahead and do that. We know that, so I dropped the altitude from P to AF, and I just call that H because that's usually what they use for the altitude. But okay, so we know that in a 45, 45, 90 triangle, the two legs are equal, so because it's isosceles, of course. So PH is equal to HF, right? And we also have our 30, 60, 90 triangle, but we'll get to that. So what we actually want to find is PA, because this is the side length of this. We already have this length in PQ. We want to find PA, so we can relate PA to PQ, which we know will be the ratio of the two triangles. So we want to find PA. That's our goal. Okay, so what we can actually do here is we can call AH X. So since AH is X, HF must be 1 minus X. Seeing that it's a 45, 45, 90 triangle, PH is also 1 minus X. So we can write that as well. Okay, and now we can write out a sort of relation. We know that in a 30, 60, 90 triangle, the ratios will be in 1, root 3, and 2. So we can use this relation to solve for x. So let's actually write that out. We know that PA H equals root 3 times AH. So we can actually substitute some of the values, and I'll show you that math when I get back. Okay, so as you can see here, I've written out some of the math that went on. So because of our 30, 60, 90 triangle, we were able to find a relation between the sides, and since we call them x and 1 minus x, we were able to create this sort of relation. So here we have 1 minus x equals root 3 times x, and we move over both x's to one side, factor out the x, and isolate the variable, and we get x is equal to 1 over 1 plus the square root of 3. We want to rationalize the denominator so that our value for x looks neater, plus it'll be easier to do our calculations with a rationalized denominator. So I multiplied by the conjugate, which is root 3 minus 1, and basically I'm using the difference of squares to rationalize the denominator, and here I get that x is equal to root 3 minus 1 over 2. So we know that AH is equal to root 3 minus 1 over 2. So what does that make AP? We know that AP is 2x because of the relations in the 30, 60, 90 triangle. So that means AP is actually equal to root 3 minus 1. So we can go back to our bigger diagram and label that over here. Root 3 minus 1. So we want to find the ratio between triangle PQR and triangle PAF. So we want to know what PQ over PA is. So we can do that over here, because we know what the side lengths are. PQ actually equals root 3 plus 1, because we know that AQ is equal to 2. We can add up the segments. PA is root 3 minus 1, and what we can do here is actually rationalize the denominator. So we multiply by root 3 plus 1 again. And this comes out to be, we have a square on the top, so 3 plus and we can simplify this to 2 plus root 3. Okay, so this is nice. We now have the relationship between the two sides. So we know what the ratio of similarity is. Now, in geometry, there's a similar figures theorem that lets us determine the area of similar figures. So if we know the area of one of the triangles, we can find out the area of the other, because we have the ratio of similarity. Now, the theorem states that, say if you have two certain polygons that are similar, the ratio of the areas is actually the square of the ratio of similarity. So we need to square this, because we are going to use the similar figures theorem. So we know the ratio is 7 plus, or the square of the ratio is 7 plus 4 root 3. So now, to find the area of triangle PQR, let's finally write out what our plan is. This is actually equal to the square of PQ over PA, as I mentioned, times the area of triangle PAF, because they are similar. This follows the similar figures theorem. So we have one component of this equation, we're just missing the other one, and that is the area of PAF. So let's actually go back to the other triangle. So here we're actually back at triangle PAF because we want to calculate the area of it. So now what I have here is actually a well-known equation that is used to calculate the area of a triangle, and that's 1/2 AB sine C. So if you actually have like a triangle with angle C, so let's say this is C, and you have sides AB, you'll be able to calculate the area of that triangle because you have all the information you need. So here we're going to use AF as A, AP as B, and angle A as C. And this works because the two sides are sandwiching the angle, which is the correct way to use the formula. So we know that AF is 1, AP is √3 minus 1, and angle A is 60 degrees. So let's actually write out specifics of our formula. This is always a good thing to do. And now we can do our calculations. AF is simply 1. AP is √3 minus 1. And sine A, which is sine 60 degrees, is √3 over 2. So this gives us that the area of the triangle is 3 minus √3 over 4. Now, we can go back and we see this equation. So now all we need to do is plug in our components. And then we can find the area of PQR. So you get 7 plus 4 √3 times the area of PAF, which is, as we solved, 3 minus √3 over 4. And you can do the math, and I'm not going to show that because it's not too hard to do. You can do it using the FOIL technique, but the answer will come out to be 9 plus 5 √3 over 4. And this is the area of PQR. The answer will be in the form A plus B root C over D, which is actually what we have here. All we need to do is find A plus B plus C plus D, and that's 9 plus 5 plus 3 plus 4, which is 21. And as you know, on the Aime I, you actually have to bubble in the lead digit. So if it's a 0, if the lead digit is 0, you have to do that, otherwise you get the answer wrong. So the answer is actually 0, 2, 1, and that is our final answer to this number 12. And so yeah, I mean, it was a pretty complicated process, but today we actually learned that drawing a very neat diagram is important because it lets you see things that you probably might not be able to see, and that, you know, these complicated like problems late in the exam, they can actually be solved with you know, very, very elementary ideas that I showed you. So I hope you guys enjoyed the video and were able to get something out of it. And if you have any questions, feel free to let me know in the comments. I'll be more than happy to answer them. Thanks. Bye.